I gave you, or I have here the introduction section of the lab guide plus the instructions for today. I'm going to go through a few of the things from the lab guide, things like how the reports work, and then go over the lab. So starting off, the things that I'm looking for in lab, I want students to develop good habits on how they measure and record data and on making graphs. So we're going to have a number of graphs throughout the semester. Learning about precision and error analysis, how you keep track of error. That's going to be, and actually today, these are things we're focusing on because we're going to be using them throughout. Interpreting results. And I hope that as we go through lab, you become more and more curious about why things work, right? That's what physics is about. Trying to understand how things work and why they work. And the reason we do lab is so you don't fall into the dangerous trap of believing your teacher. Right? You have teachers in all kinds of subjects, and some know the subject better, some know them worse, but all of them are imperfect. And I'm certainly an example of imperfect. And so when I'm teaching you, you should not say, oh, he says it's so, so it must be so. Right? That's an appeal to authority. It's a logical fallacy. It's important that you think things through and conclude for yourself, yeah, that's how it works. And so in these physics labs, we're going to be doing things, doing experiments, so you see that it actually works that way. You know, oddly enough, physics research shows that even among your very best students, you give them a test and they can pick out the right answer and the right explanation. But then if you ask them to explain how it really works, they say, well, yeah, that's what the teacher wants, but this is what really works, and they'll give you a wrong answer because they're not actually convinced about how it works. They're smart enough to learn to parrot back what the teacher says, but they don't believe it. And so lab is your chance to see how it really works so that you don't, have that dichotomy of this is what teacher says and this is what reality is. They should merge together because honestly, I try very hard not to teach you falsity. That's not the goal here. I want you to have fun in the class. I don't want you to leave lab having lots of work to do in lab. I know you have homework every night, and that homework is going to be a drag. It's going to take a fair amount of time. I don't want lab to also be a drag that takes a lot of time. So my goal is that when you leave the lab room, you should have everything done. You don't have to go worry about it and rewrite it and do that kind of thing. So as I go through the lab report, I'll talk about the way it works and how you should be done. So the lab report, it's not a lab notebook. It's just you take it on paper. You're going to scan that paper and submit it on Moodle as a PDF document, one PDF document. So you'll need to merge it into one. You should start with having the title of the lab. So if you look at today's lab, it's measurements. And so you have that title, and then you also need to have your name and your partner's name and the date on which you did it. So you'd start off and you'd have, your paper has here measurements. Yeah, you can read my writing. Richard Webb. Yes, I only put one R in Richard when I write it because I am that kind of lazy. And my partner will be my wife, Amy Webb. And the date, 8, today's the 22nd. Right, so that would be the title, the name, and date. The purpose is, what we're trying to get out of this lab, what my goals for this lab are. You can just quote verbatim the purpose. Right? I just want to make sure that it's clear in your write-up. I want your write-up to be something that's a standalone, something you could show your parents, and they're like, well, gee, I don't even know why you did this. What were you doing anyway? I want it to be so they can read the write-up and they know what you did and why you were doing it. Then you have the scientific method part. The scientific method part will start with an observation. Today's observation has to have something to do with falling. And I don't mean falling like trip and fall necessarily. I mean, I see the Olympic diver dive off of the platform, dive off the 3-meter board, whatever. And something about that you found intriguing, wondering why did that happen? So the observation, it's very broad, but it should be something that you can see some kind of regular basis and that piques your curiosity and can be explained with the theory of the day. So our theory of the day, it's very clear. It says that it has to be something that you can test by comparing the times for a ball to drop 1 meter and 2 meters in height. So your theory should have something to do with the time it takes for things to fall and make a prediction about how much longer it takes if you double the distance. So your hypothesis does not, I said theory, hypothesis. Your hypothesis should not say it takes twice as long to fall twice as far. It should say it falls because of this, and then that predicts. And so I have an example here of an observation. When my roommate slams the door, my phone sometimes falls off of the shelf. I can catch it if it's on the higher shelf, but I can never get it fast enough if it's on the lower shelf. Right, an observation. And then my hypothesis would be something to explain that. So because of a constant, and the hypothesis is absolutely wrong here. Your hypothesis can be wrong. I want you to try, but I'm not going to grade you on having a wrong hypothesis. I mean, science is built on wrong hypotheses. You get a wrong hypothesis, you test it, you find it's wrong, and you get better and better. So because the constant air resistance, the speed of the falling ball decreases linear with distance as it falls, this predicts the time, anyone who knows much physics can see that's palpably wrong, but it makes predictions. And so then you have the test. This is how I'm going to test it. And your test should say what result will confirm your hypothesis, what result will disprove it. So you need to say what your test is going to be. Today, the test will be, I'm going to drop a ball 1 meter and measure the time, drop the ball 2 meters and measure the time. And then you need to say what outcome will confirm, what outcome will disprove your hypothesis. So that's the first section there, the scientific method. Any questions about the scientific method section? Now, one little idiosyncrasy here. If you show it to me and have me sign off, I'll read it and I will do a quick grading like, oh, that makes sense, yeah, it's good, or, ooh, you got a problem here. If you get me to sign off on it, then when I come through, apparently because, as I said, the TA fell through, grade it, I won't regrade, I'll just give you credit because I already graded it in class. If, I will be busy since I'm here and there's 28 of you, if you feel confident and just go ahead and go through with it, then I'll just grade it when I'm grading the labs. Okay, next, equations. Every equation that you're going to use should be listed in the equations section along with definitions of the variables. So for instance, an equation that we have for today's experiment is volume is equal to 4/3 pi times radius cubed. You might put it in there with diameter instead of radius, but and so then you'd say where V equals volume and R equals radius. Right, so every equation needs to be written like that. And in your lab, you have to have an example of using each equation. So when I'm going through grading, if you put your example in a box or something so I know, oh, here it is, it'll make it easier for me to grade because I need to find an example. Only one example. If you do the same calculation 20 times, use a spreadsheet, okay? Don't go typing in your calculator for a half hour. Use a spreadsheet. You make the formula once, you copy it down, and all the calculations are done. It's much quicker. If you can do the calculation once, I'm really confident you can do it 19 more times. Apparatus, list the non-trivial apparatus. Non-trivial will depend on the lab. For today, everything's non-trivial. The meter sticks are non-trivial. From now on, meter sticks will be trivial. You'll say, oh yeah, I got a meter stick. Duh, you use something to measure distance. That was probably a meter stick, right? So list all the equipment that you're going to use, and then you have the experiment. You have a lab guide that's written by a very verbose person, otherwise known as me. And so you have instructions that are really long. Don't write those long instructions. Don't write A, B, C, D. Summarize them so that somebody who's reading could reproduce it with a certain level of, expertise. But not every minute step like I've given you. So you should never have your experiment section take more than half a page. Whereas in the lab guide, it's like 3 pages, So you want to condense it down and you want to give the bare bones so somebody can follow it and do it. Everybody understand? Jordan, our TA, he's not here, so we can, he was teasing me yesterday. On his test, he wrote just enormous answers to every question. So he said he's going to tell everybody to do that on the test. And that'll make my life harder. No, you don't have to do that either, just in case he does try to tell you that. Data calculations and discussion. The data calculations and discussion is the stuff that you can't do before you come to class, right? Everything up to that point you could have done before you came, right? It's in the lab guide. You can just go along and do it. The data calculations and discussion, you can break it out into pieces if you want, but I think it makes the most sense to just make it one section, and it should be in chronological order. That is, you should just go through and have things in the order you do it. So you do something, you write it down. Do something else, you write it down. You just keep writing as you do things. You don't do a bunch of stuff and then come back and try to write it later. So when you take data, you write the data as soon as you take it. That way it doesn't get lost. Your data should always be in data tables unless it's only a one-time measurement. So for instance, today you're going to be measuring the diameter of a ball 5 times, I think it is. So you'll make a table, and I'll show you how to make that data table when we get there. But you want to make it a table so it's easy for you to look at the numbers and scan them, see if they make sense. Easy for the grader to find them and look at them. If something goes wrong in the experiment, you should just make a note of that at the time it goes wrong. You know, this work went wrong. I had to do it again, had to change this. You should have that kind of detail in there. And your calculations, when it comes time to do calculation, just do the calculation, just where you are in your continuing sequence. After you're done with the experiment, we have the results section. Results are the important outcomes. For the first experiment, I tell you exactly what the results are. Usually, I'm going to leave you to have some thinking about what was an important result. Each individual data thing that you measured, that's not your important results. The average for the radius of the ball, or diameter of the ball is what you're measuring, that's an important result. The average of the diameter. The mass of the ball, the average that you got, that's an important outcome. The density of the ball, that's an important, those are what you're putting in for your results, not each individual measurement. Everything in the results section should have already appeared in the data calculations and discussion section, right? So the results is nothing new. It's just summarizing these were the important outcomes. And then the conclusions are the things you learned. So conclusions, what went right, what went wrong? Did you achieve the purpose of the lab? Was your hypothesis confirmed, or did you disprove it? So those are the things that go in the conclusion section. I swear I had more here before. The scanning is out of order here. This is how I'm going to grade them. This has a breakdown of points. For the first lab, I'm going to try very hard to make sure that you learn and don't just lose a lot of points because you did it wrong the first time. Because you're learning, right? You don't know exactly how it's going to be graded until it's got one under your belt. But the way points will be taken off is given in this here. So there's a total of 2 points for the header, 3 for the purpose. You better get those 3, right? Because you just copy one sentence verbatim. 20 points in the scientific method, 5 for the apparatus, 5, and so on. And so I will be going through and applying these when I'm grading. And you can see that the results and the conclusions, they're pretty important. The data is pretty important. If you skip something, that's going to be the most devastating to your grade. If you do something and you're sloppy, that will take off a fair amount. If you do something, you're careful, but it's still wrong, that's going to be a much smaller deduction, right? Because honest mistakes happen. And often with the honest mistake, you can fix it. If you're sloppy, well, there's not a good excuse for that. So I've talked about now the lab report. Any questions that you have about that lab report? Yes.
Are these lab reports being recorded in like a lab report notebook or just
just on paper, and then you're going to turn it in as one PDF document, which brings up what I'm going to go to next on the PDFs. But yeah, you put it on your own paper, and then you're going to scan the PDF and combine.
So are you and your partner going to turn into individual?
Yes, each person turns in their own report because you have things, like in this one, you're going to have, this is my data, this is my partner's data, questions about mine, questions about my partner's. And of course, the conclusions are going to be your conclusions. Your partner's conclusions and your conclusions are not typically going to be the same conclusions because it's what you learned, not what your partner learned. Corso. Okay, when are they due? They're due Thursday night, just before midnight. So today is Tuesday, and so you have until Thursday night to turn them in. That's so people have time to go get it scanned. Right? You should have everything done when you leave. You got 2 days to get it scanned and turned in. You had a question?
I think that was kind of my question.
Okay.
The scientific method, you said some stuff can be done before lab. Does it like explain what you're gonna do and then you make it into a scientific method or what?
Well, the lab guide tells you basic instructions on what you need for the scientific method. And you have the discussion of the procedure. And so you have everything you need to determine what you want to do for the scientific
So
method.
You can make the scientific method before.
Yeah.
Oh.
Noah, I know your name.
Should or can any of this be typed? Do you
It could be if you wanted. It's obviously easier to grade if it's typed. My concern is it takes more time for you to prepare it if it's typed, and I don't want people to spend extra time. So I'm not going to take anything away if it's typed. It's just I encourage you to try to be economical with your time.
So this is due before each after a lab.
Yes.
So this is laboratory every week.
Yeah. Anything else? Okay. I redid this portion after I printed the lab guide. So this is different from your lab guide, and it's not yet enacted. Hooray. We got new copy machines this summer, and that's why this section had to be changed. And with the new copy machines, for us teachers, we just take our ID card, we slap it on this thing, and it knows who we are and lets us do stuff. They are going to make some ID cards that will be attached to the copy machine here on this floor, on the floor up above us, as well as in the library, to allow students to use the scanning functions in the copy machines such as we need for the lab. And so these are the instructions. They said it was going to be blue. They haven't been made yet. They're not there, so they may not turn out to be blue. But they're supposed to be blue cards that they're just going to attach to the side of the copy machine. And so you'll start by taking that blue pad and taking it to the little lighted sensor. And that will log you in so you can scan. And then you could either scan to a USB drive or you can email it to yourself. So that's a choice. Either one works. If you want to use a USB drive after you've logged in, you just stick your USB drive in. Once it is mounted, it'll pop up with a menu that has 3 options on it. You choose the center one, which is save a document to external memory. You can set the file name if you want, and then you just do the scanning. If you choose to do the email to yourself, you click the fax scan button on the machine after it's logged in, and then you select direct input so you can type in your email address. You type it in. If you want to change the file name subject, there's a button to do that. And here's the scanning instructions. If you're scanning single-sided sheets of paper, you can put them in the document feeder, put the top one on top. There's my wife. Hi, Amy. It brightens my day. Put the top one on top and put them so they're facing up. And you just hit start. It'll scan them all and either store them on the USB drive or send them to email, whichever one you chose. If you have double-sided, you need to change it from single-sided to double-sided. So you'll need to hit the simplex duplex button and choose 2-sided instead of 1-sided. Everything else the same. And then there's some more complicated. If you want to do multiple single sheet scans, like you have everything here and you want to put it on the bed, I have the instructions for that here too. So those are instructions for using the scanners to get your PDF files. Some people use their smartphones. Generally, that's not as good, but as long as it's readable, we can still grade it. I have this random hope that somebody besides me will be grading at some point. Of course, when we do things in lab, we're going to be using like computers to collect data and computers to make graphs. And so how are you going to get those graphs combined with your scanned notes? If you have a Mac, it's actually not hard. You can just drag and drop. You open it up in preview and drag the page from here to here, and it does it. If you have a PC, this is the software that I use in my office, PHYS fill, PDF tools, and it allows you to separate documents, to combine documents, to rotate documents, all kinds of things. Alex has a year of playing around with that for me. So, you can always ask Alex if I'm not around how to use it. Right, Alex? Yes. He totally wants to give you his free time. He'll bill me for it.
I gave up on your program after a semester.
Did you really?
Yeah, I had to use an online one because I just didn't know how to use it.
Oh, that's confidence
So
building.
You can ask me.
You can ask him.
Direct you to the one that I use.
Okay, so maybe don't ask Alex. You can ask me. It's doable. So it won't allow you to upload more than one file. That's intentional because I want to be organized. I don't want to be a whole bunch of random pages and I have to try to figure out now what goes where. I want to be organized in one file. Okay, then we get to errors. So discussion of accuracy and precision, I don't need to go over that. How do we keep track of errors? If you want to be careful, you keep track of errors by looking at the percentage of error in this and the percentage of error in this. And then when you do calculations, you can propagate that percent error. And so the calculation for propagation of percent error is shown here. It's also shown in today's lab guide. So if you have like 5 items and each one has this error, and you multiply 5 times that, well, the error is multiplied by 5. No problem. If you add or subtract, then the errors are added. If you multiply or divide, it's the percentages of error that are added. And if you take to the nth power, you multiply the percentages by the number that you did. If you look at the equations, they don't look that hard, but it's kind of a nuisance to do this over and over again. And so because of that, in science, we generally just use significant figures. And so significant figures have rules, and the only 2 that we pay attention to are these 2 rules here. The ones for addition, subtraction, and multiplication, division. My son is a freshman or a senior in high school taking physics, and so he just had to go over this in his class. I go over it in my class. What I find is virtually everyone knows one of these rules. Virtually everyone knows how to deal with that. Very few people know how to deal with addition and subtraction. So let's go over those rules. Addition, subtraction. Now I should start off with what's a significant digit or significant figure. A significant figure is a number that carries meaning. So if I write a number like 800, those trailing zeros may or may not carry meaning. I could say the number of students is about 800. So I write 800. But it's not exactly 800. And so I could have rounded off to the nearest 10. If I rounded off to the nearest 10, then this one here would not be significant because it's just holding the place. If I rounded off to the nearest 100, then neither of those holds significance. So writing down 800 is itself ambiguous. It could be 1 important digit, 2 important digits, or 3 important digits. How do you indicate if it's 2 or 3 important digits? Do you know? Okay, if I put a decimal point, if I do that, that decimal point means all of the numbers that I wrote to the left of it were significant. What if it's only 2 significant digits? Anyone know how to write if it's 2 significant digits? Alex?
80 times, or 8.0 times 10 to the second.
Okay, scientific notation. Every digit is significant in scientific notation. And so that's one way to do it. And Corso, I think, said the other one, put a bar over the last significant digit. So those are significant. Now that's easy. What about 0.0030? Which digits are significant in that number? Okay, rule number one, every non-zero digit is always significant. So the 3 has to be significant. But let's go like that, 30-30. Rule number 2, a 0 between 2 significant digits is always significant. So these 3 have to be significant. What about the zeros on either side? Okay, trailing 0 is if it's on the right of the decimal point. If it's on the right. So this one here is significant. Why? Because if you took that 0 away, the number wouldn't change. It'd be the same number if you took it away. So the only reason to have it there is because it's meaningful. So that makes it significant. The leading zeros here, those are not significant because they're placeholders. They're just moving you to the right place. If you took one of those away, the number would change. And so their point is simply to get it to the right number of decimal places. And so this number here has 4 significant digits as I wrote it. This one here has 2, this one here has 3, and of course, we have the ambiguous one. So identifying what's significant and what's not is something that will come up on the first exam. Then we have the rule for addition, subtraction. And that rule says mealy mouthed as can be. Okay, so the greatest of the least significant digits in the original numbers is the least significant digit in the answer. Yeah. What? It makes perfect sense, but you have to go slow and understand what each piece means. So the least significant digit. The least significant digit is the digit farthest to the right in your number that is significant. So for instance, in this number here, that is my least significant digit. In this number here, because it's ambiguous, I don't know. So let's say that it was 1, that would be the least significant digit. This one here, it would be this one. This one here would be that one. It's the farthest to the right that is significant. So for every number, you need to determine which digit is its least significant digit. And then the greatest one of those is the place in the answer that's significant. Now, to me, this is much easier to understand just with an example. So let's say I'm going to add this. The first thing I do is identify which one's the least significant digit. Let us assume that this is not significant. Right? Because it's ambiguous, you have to have some way of determining that. So once I've determined that, what I do is I stack the numbers and I identify the least significant digits for each one. And I say, which is in the greater place, that 7 or the 3? The 7, because it's in the tens, whereas the 3 is in the units. So I just draw myself a little dashed line here that's separating my significant from non-significant. And so everything that's on the left of that divider is significant. Things on the right are not significant because that 0 is not significant. So what is the correct answer to this addition? It's 5690 because that 3 was not significant. So, do what? Are you saying why not just use 5693? Because that 3 is meaningless. It could be 5697 for all you know. Right? Because this 5670 could be 5674. Because this 0 is insignificant, you don't know if that's a 0, a 1, a 2, a 3, a 4. And so you can't assume a value to it when you don't know it.
Is it kind of like when you look at a ruler and then you say, okay, 56.33, you make an estimate around there, so is that what it's talking about, like that one, you like kind of making an estimation of what it is? So
With the significant digits, it's not exactly the same thing. It's based on the equations that are on the other side of the screen here. They're percentage equations. The significant digits is not perfect, but it's a quick way of trying to keep track of your precision, how much uncertainty you have in your answer. And if it's 5670 and I don't know this digit, I don't know it's 0. It could be 5666 for all I know, because I only know it's good to the 5670. It rounds up to 5670 or down to 5670. I can't just make up a value for this. I can't say, oh, well, I'm just going to use 0 and say that 0 means something. So if I take a number that I don't know what it means and add it to a number I do, I can't say, well, now I know what it means. It's like infinity plus 5. How big is that? It's still infinity, right? Because we don't know what the number is.
So you're just writing down the ones you know, and then the other ones you would just put like for there you would know.
And then I put in 0 for the.
You put in a 0 because it's a number, but you don't know the rest.
Yeah.
Okay.
So when you add and subtract, that divider there, finding the least significant digit in each number, and then just taking the greatest of those, and that's the least significant digit in your answer, is the rule for addition and subtraction. Everybody can probably quote to me, what's the rule for multiplication and division? No? Most people know that one. For multiplication and division, the lower number of significant digits in original numbers is the number of significant digits in the answer. So if I was multiplying these two numbers, one of them has 3 significant digits, one of them has 2. What's smaller, 3 or 2? 2. And so my answer would have 2 significant digits. So the multiplication division is a simple rule that most people know, but most people didn't pay attention or didn't learn the addition subtraction rule. And so we need to know both of them, because you will have something on the test that deals with this, knowing how to identify significant digits. The whole reason for significant digits is to make life easier than it would be using these equations that are circled in blue. Yeah.
Just how you worded it.
Which one?
With the multiplication and division. I was halfway. Okay, go ahead.
Okay. As some students have figured out, I shared the OneNote thing so you can look at everything. You can actually look at it as I'm writing. It shows up for you, right? So you can follow along in your computers as I'm writing and have it in perpetuity. Yeah. Okay, maybe that's not so awesome, but let's move on. I have here all the rules for significant digits to try to explain how they work. Graphs, we'll talk about that later. And so let's get to the lab. So measurements, our purpose, what you would write down for purpose right here, to learn how to read simple instruments and how to handle uncertainties in measurements. Why I spent all the time on the uncertainties there. And I have some examples here. You can read the introduction. So first, how do you determine your uncertainty if you measure something like with the meter stick? If your limiting factor is the meter stick, then what I have here works for you. But sometimes the limiting factor isn't the meter stick. Like let's say I want to measure the length of this bag. I put this bag on the meter stick and I try to measure it. What kind of difficulties do I have measuring the length of this bag? Okay, it's flexible, it stretches. The edges are rather ill-defined. Depending on how I squish it, the edges will be different positions. The edges aren't even touching the meter stick, so I have to kind of eyeball it. Those are all factors that are going to affect how accurate I can be, how precise I can be, more precisely, with my measurement. And so I need to think about this and think, how much error do I have just because of the type of thing I'm measuring? And with this, I would say my error is probably on the order of 0.5 centimeter, just because of the nature of the thing I'm measuring. Now, if I look at the meter stick is marked off in centimeters and then in tenths of centimeters, also known as millimeters. And so it's marked off in millimeters. I could certainly read to millimeters if it was just the meter stick. Well, when you're making a measurement with something that's like this, like the meter stick, it's not going to be exactly 1 millimeter or exactly 2 millimeters or exactly 3. It's probably going to be somewhere in between. And so we estimate one further digit. So that last digit is going to be an estimate, and we have to determine how accurate we are on that. Now, there are some people who are more aggressive, some who are less aggressive. I tend to be less aggressive. That means I give myself a bigger uncertainty than is probably necessary. But I say, for a rule of thumb, I can probably determine very accurately up to 1/4 of the distance between the two marks. And if I do to 1/4 of the distance, 1/4, of course, is 0.25. Rounding that to one digit, that's 0.3. So I would say I can read this to 0.3 millimeters. So my uncertainty with this instrument is 0.3 millimeters. My uncertainty with this is 5 millimeters. What do I do for my actual uncertainty when I make a measurement?
Base it on the most uncertainty.
Yeah, based on the most uncertain. So I'm going to go with 5 millimeters as my uncertainty if I'm measuring that because of the nature. But I have to think about all the things that could affect it and then deduce how much this could contribute, how much that, which one's the biggest, what's my uncertainty really going to be. Other things, never use the end of the meter stick as a reference point when measuring. Why? Because they're not calibrated. On some of the meter sticks, you can actually see where the 0 mark is printed on the meter stick. It's not at the end of the meter stick. So you don't use the end of the meter stick. So I measure like from 10 out, and then I have to remember to subtract 10 from the number that's shown, so that I'm not using the error that we know is present at the end, right? Get rid of any error you can get rid of. So you're going to use the meter stick to measure distances, and if the meter stick is the limiting factor, what's missing in this number? Units, right? I come to it later, I point that out. But this would be 86.56 plus or minus 0.03 centimeters for the measurement shown here. It shows out to, we know it's between 86.5 and 86.6. I estimated that it's 6/10 of the way between the two, but I know it could be easily 8/10 or 5. Well, it's probably not 5/10, right? Because I err on the side of giving myself a bigger uncertainty. So with this, traditionally I use 0.03 centimeters unless there's a difficulty with the item we're measuring. Today you're going to be measuring steel balls. There's likely to be a problem besides the meter stick in your uncertainty, right, with the steel ball. And so you'll need to think about and analyze that as you're going through the experiment. Next, we'll get to the, see, I told you that's repeated, Vernier Caliper. I skipped over the Vernier Caliper. I had the picture somewhere. Where is it? There it is. The Vernier calipers is a more precise measuring device. This is a vernier caliper. The vernier has to do with the spacings on what you read. The calipers are these things that stick out. This here is for measuring an inner size. This is for measuring outer size. So if I want to measure, let's say, the diameter of this pen, I put the pin in here. Let me point out something that would be a problem. See that gap that I can see you through? That's clearly not touching together when I close the faces all the way. Don't put your item in that gap. You're not measuring it if you put it in there. You have to put it out between the parallel faces like that. You put it in there, you squeeze it up, and then you read what it says. So here, we can zoom in on a vernier. And the first thing you do, that's 0. That's 10. That's 5. So you look where the 0 hits. Now, if this is 4 and this is 3, this one here was 3.5. So where's that 0 hitting? Okay, it's between 3.4 and 3.5. So we know it's 3. That's not a 4. 3.4 something. 3.4. And if you were estimating, you'd probably say 3.46, 3.47, right? But with the vernier caliper, you don't estimate at all. Because the vernier caliper has, going from 0 to 10, in the space up above, notice this was between 3.4 and 3.5. You go over 10, it's between 4.3 and 4.4. You have the spacing down below is 10% smaller. So that you have 10 lines down below in the space that has 9 lines up above. And so because of that 10% offset, you simply look down below and you say, which line in the bottom portion matches up best with any line up above? And this one here is the best matchup. Now, some people might have said, no, I think it's this one, or no, I think it's this one. No one would have ever said further than that off, right? The furthest you could be off is by 1. So your uncertainty is going to be plus or minus 0.01. So we have basically 1/3 the uncertainty. It's a better measurement. And so how do I get my actual number? Well, this was 5, 6, 7. You just read which one it is on bottom that matches up best with any line above. So the vernier caliper gives you a better uncertainty because of the design of the instrument. I didn't point out, it also has a depth gauge. This here is for measuring depth. So, like that. So today for our measurements, we're going to use a timer to measure time, meter stick, and vernier calipers to measure distance. So now I'm ready to get to, let's do the experiment and get done. There we go. So for the experiment, the equipment we need is the vernier calipers, the meter stick, metal ball, and triple beam balance. Here's a triple beam balance. Before we start with the experiment, I'll show you how to use the triple beam balance. First thing with the triple beam balance, it works via torque balance. You want to make sure that it's zeroed properly. So make sure each one of these sliders is actually in the 0 position. They can be slid beyond the 0 position. That's not in the 0 position. You see this thing is moved in the wrong place. Get them in the 0 position, this one all the way over. And then when it settles down, this indicator should point at the line. Now I can't see from here, so I can't tell. But anytime you use a triple beam balance, you need to zero it before you start. The person before you may not have. I'll tell you right now, we're going to have a lab final at the end of the semester, and one thing you're going to have to do is measure the mass of something, and it's not going to be zeroed when you start. You're going to have to remember to zero it, then make your measurement. So how do you zero it? If this is pointing the wrong place, still can't tell from here. You have a screw here that you can screw in or out. that will adjust where that points. And so now it's clearly pointing too high. And so if it's pointing too high, I need to screw it in. If it's pointing too low, I need to screw it out. Then to measure the mass of something, I put that object on here. And I know that it's less than 100 grams, but I start by putting the 100 grams one out here. It went down. It means it's less than 100 grams. Bring it back. Let's go to the 10. More than 10 grams. Bring it out to 20. Less than 20, so bring it back to... Actually, I don't know which one I'm on. I'm on the wrong side. I think that's 20. And that should be... I don't know. It's on that. It's between that one and the next one, whatever number it is. And then you take the last slider, you slide it across, and you adjust its position until it's pointing out to 0. Now, of course, it's not even 0 now, so this would be a nonsense measurement anyhow. But you see how it works. When we make measurements, I always encourage you or require you to take at least 3 measurements. Why take 3 when 1 gives you the number? Yeah, to make sure you're reproducible. If you made an error once and you didn't make it the next time, you would see that. So if you take 3 and they're all consistent, you can have better confidence. Now, to take that measurement, I don't go, yep. What I do is I take this off, I move this, put it back on, slide that back to make sure that I've reset the system and I'm actually making a new measurement and not just putting it back on. So that's how we use the triple blue balance. Now for what we're actually doing, I've already talked about the scientific method stuff. For the procedure here, there's a worksheet on the laptops, which I go ahead and open up the laptops and at least start them up. Then we can log them in. They will take probably 5 minutes to start up, so go ahead and do that now. They're not the world's fastest laptops. They were slow when we bought them. The first thing you're going to do is start with some timing. So for each group, and you're going to work in groups of 2. So there's 2 lab rooms. There's one beside us over here. Some people will go in there. Just for your information, this room I control, that room Dr. Seth McNeil controls. And here I keep the thermostat 69. I'm still sweating copiously. That one he keeps it like a 74. So if you're cold in here, go in there, it's warmer. If you're hot in here, I'm sorry, I am too. So what you're going to do is you're going to estimate, before you do any dropping, estimate how long you think it'll take for this ball to drop 1 meter. And so then you're going to write down in your lab book, I think it's going to take this long for it to fall 1 meter, and give your reason why you came up with that. Now, this is an estimate. Are there wrong estimates? Yeah, if you say it's going to take an hour, you will lose points there, okay? I mean, you're allowed to be wrong, but not ridiculous. So after you come up with this estimate, and please, do the estimate before you do any dropping. Then without timing, take the meter stick, hold it at the top. You don't need to be exact, so we're going to use the ends of the meter stick, even though in this one here, the ends of the meter stick are very clearly not calibrated. And then you're going to drop it a few times without timing, and then just use your judgment. Was my answer reasonable, or was I too long or too short? How would I modify it? And give your reasons. And then your final thing before you actually make measurements is, how much error do you think you may have? How far do you think you could be off with your final estimate? Now, after you've made all those estimates, then it's going to be time to actually do the measurements. So let us suppose, what's your name? Marka. Marka and I are partners. And so first we're going to have Marka measure how long it takes for it to drop a meter. So she's going to sit here with, actually, no, we won't do it as the example because then everyone, well, here. We'll do it with a non-meter. Come on up here. We'll do it with not a meter. And that way, people won't be able to say, oh, look, that's what the correct answer is. So you have on the laptop, once it's logged in, you'll have a Physics 151 folder. You double click on that. And in here, you're going to use the General Physics Lab spreadsheet and the timer. So, excuse me? Alex will show you. Alex will show you everything while I'm doing other things.
We're just logging in.
Yeah. Okay, so I double clicked on the timer. You see this timer that it brought up down here? This is the timer I provide you. You can use like your smartphone if and only if your smartphone provides 3 digits past the decimal. If it only does 2, then you need to use this. The iPhone only does 2, sadly. Okay, so what we're going to do, how this timer works, around here, Marka. You hit space and it starts timing. See the numbers going up? You hit space and it stops timing. Tricky, right? If you hit space again, it will both reset and start over. So I hit space again, it starts over from 0. So you don't have any lap function, you don't have a reset button. So what we're going to do, I'm not even measuring this, I'm just going to have Marika time it. So you look at me, you ready? Mm-hmm. Now when I drop it, you start it. When it hits the ground, you stop it. Right? So I drop it. Okay, so there's your timing. And then now before you go on, you would write in your book that time. And then we would do it again and again and again. That would be Marika's measurements. So we go in my lab report, I'd say my partner's data. And then we switch spots. So then she's going to be the one dropping it. I'm going to be the one pressing the button. And so there's my time. Now, we weren't necessarily even the same height, but that's how you do the measurements. Pretty easy, right? So that's it. So each person is going to make their own set of measurements. I think it says 5 measurements. When you have those 5 measurements, they should all be put in your data table as you're taking the data. And then you're going to put them in your spreadsheet. So in the spreadsheet, we'll put in our time. So I'm just making up numbers. And it calculates for me the average and the standard deviation. Now, how many significant digits did we have in our measurements? We had 3. So in your lab, report the average with just 3 significant digits. So in my case, 0.4894 of my made-up numbers, I'd round that to 0.489. What are my units? Seconds. And what would my uncertainty be? Now, the uncertainty in my measurement is going to be 0.001 second. And so that's why I'm going to actually put here 0.001 second, because this timer is good to 0.001 second. Now, the uncertainty in the actual number is much bigger because we have things like my reaction time involved. So we'll put 0.001 for our times here, but then we're going to compare the uncertainty that we estimated with the standard deviation here. Now remember, these are made up numbers, so there's no meaning to any of these numbers. And once again, just to use 1 digit, so I would put 0.3 if this is what I got for my standard deviation. I don't need the rest of it. Now, how do we record this data in our data table? Your data table should look something like this. I didn't give myself enough space. Let's trial. Richard. Time. You're right. Okay, so I only have 3 there, but I put my data like this. Now notice in the data table, do I have units? I do because I have them in my column header. If you put the unit and the uncertainty in the column header, it's assumed that all the numbers under that column have that uncertainty and unit. So I could put it like this and save myself a lot of writing, or I could have not put that there and put plus or minus 0.001 seconds on each one. Either one works. I can tell you which one I would do. Whoops. So you need to have the uncertainty and you need to have the units there. You put all the numbers in, and now in this case you use the spreadsheet to do the calculation. You don't have to put the average of standard deviation equations in your lab guide for equations, and you can just put down here average standard deviation and just put the numbers in there. So that's how you record the data. Now remember, as you're dropping them, if you have problems, like Richard kept dropping the ball sideways, you write that in the lab guide. That's something that went wrong. Anything that's marked with a Q-C means that it's a question or comment that you need to make. Now, I told you in your experiment, when you're describing what you're going to do, don't put down A, B, C. Put like Roman numeral 1, this section, but don't put part A, part B, part C. But do put like Q-C1 in your answer, so it's quick and easy for the grader to identify, here's where the answer. But your answer should be complete. So QC1 says, before you do experiment, estimate how long you think it will take for the ball to hit the ground if you drop from a height of 1 meter. Record your estimate and the line of reasoning that brought you into this, or brought you to this. You shouldn't just put, 1.3 seconds because it seemed right. You should say, I estimate the time it's going to take for the ball to drop 1 meter will be 1.3 seconds because, and give your reason. Right, so you shouldn't have to look back and see what the question is. Your answer should give you the information of what you're answering. Is that clear? Right. The reason is, once again, I want somebody to be able to look at your lab report and know what each statement means, and not just have the half a statement. This is the answer to some question I don't know. And so, I gave you an example. You could put exactly what I did here, except for the XX and Y. Y would be changed to fit your theme. Okay, so you go through here. You can follow the instructions. And in the end, after you have finished all of the instructions on dropping the ball, that says to drop the ball 2 meters and take your times. Here's a 2 meter stick. Now, clearly, I can drop this from 2 meters without a problem. Some of the shorter people might have a problem. People will stand on the desk if necessary. You can do that. You only have to get one set of data for your group with the 2 meters. You don't need to have each person make the measurement. So, say I did it and Marika did it, and I had more confidence in Marcus. I say, okay, Mark, I'm going to drop it. You do the timing, right? And then you're going to use that data for the evaluation of your hypothesis. So that's Roman numeral 1, measuring time, thinking about the uncertainties associated with timing. Roman numeral 2 is about measuring the length. You're going to have each person in your group measuring the self-same ball, not getting 2 different balls. Measure the diameter of the ball using a meter stick and using the Vernier calipers. Once again, don't stick the ball all the way up at the top. Make sure it's down here between the faces. You want to make sure the ball will go through, but it is very tight. And then you read it. If you have questions, feel free to ask me. I will help you. So each student is making their diameter measurements with the 2. Make data tables. You should have your data and your partner's data. Once again, the averages, standard deviations, uncertainties. And then you answer a question about which one you have more faith in and why. Finally, mass and density. I say finally because, I'll skip the thickness of a page one. So the mass and density, we need to measure the mass of the ball. So that's why I showed you how to use the triple beam balance. So you bring your ball up here, measure the mass of your ball, and then using this equation, the volume is this, and density is, I don't see it written. The symbol for density is rho, and it's mass divided by volume. I'm sure it's here somewhere, but I don't see it, so I just wrote it. You're going to calculate the density of the ball. And notice this, if time permits. We only have 1 hour starting now, so you may not have time. Then use the appropriate equation from here to calculate the uncertainty in your density. Okay, do I have questions? It's mass divided by volume. Okay, how many people do you have in your groups? 2 people in a group. The reason for 2 is because pretty much I found if you have 3, one person sitting around twiddling their thumbs, and with 2, both people tend to be involved. You have the 2 rooms to use. Go ahead and get started.